We discussed the reflection of TE light wave in the previous class. Today we are going to discuss the reflection of TM light wave. TM stands for transverse magnetic light wave. When the magnetic field intensity of the light wave is normal to the plane of propagation, then this light wave is known as transverse magnetic light wave. This topic is just like the topic of the reflection of TE light wave. So you guys will easily understand this topic. So let us consider medium number 1 and medium number 2. Here is medium number 1. The permeability of medium number 1 is mu naught and the permittivity of medium number 1 is epsilon 1. And here is medium number 2. The permeability of the second medium is mu naught and the permittivity of the second medium is epsilon 2. And here is the interface between medium number 1 and medium number 2. This is a plane boundary between medium number 1 and medium number 2, and this plane boundary is located in the z is equal to 0 plane. So this is the interface at z is equal to 0. So if the interface is located at z is equal to 0, then definitely this z-axis will be normal to the interface. So we consider the incident wave. Here is the incident wave. The propagation constant of the incident wave is k1, and this incident wave makes an angle of theta I with respect to normal. A fraction of the energy of the incident wave is reflected back to medium number 1, and this energy is represented by reflected wave. The angle of reflection with respect to normal is theta r, and the propagation constant of the reflected wave is k1 prime. The remaining energy of the incident wave is transmitted to the second medium. This wave is known as transmitted wave. The propagation constant of this wave is k2, and the angle of transmission is theta t. And we know that the angle of incidence is always equal to the angle of reflection. So the magnetic field intensity of the incident wave is represented by Hi. Hr indicates the magnetic field intensity of the reflected wave, and Ht indicates the magnetic field intensity of the transmitted wave. So we consider medium number 1, and you see in medium number 1 we have got two waves, the incident wave and the reflected wave. So let us consider the incident wave in medium number 1. We consider the incident wave in medium number 1. The magnetic field intensity of the incident wave is equal to H naught into e raised to power minus j k1 yy plus j k1 zz and this unit vector Ax represents the, the direction of the magnetic field intensity of the incident wave, and this unit vector is normal to the plane of propagation because the propagation is taking place in YZ plane. So this is the magnetic field intensity of the incident wave, and this magnetic field intensity is in medium number 1. We consider the magnetic field intensity of the reflected wave in medium number 1. So the magnetic field intensity of the reflected wave in medium number 1 is equal to minus rho h naught into e raised to power minus j k1 yy minus j k1 zz, and this unit vector represents the direction of this vector quantity. Magnetic field intensity is a vector quantity, and this magnetic field intensity will be in the direction of the unit vector Ax. So the interference of the incident as well as the reflected wave will take place in medium number 1, and the total intensity in medium number 1 will be equal to the phasor sum of the magnetic field intensity of the incident wave and the magnetic field intensity of the reflected wave. So the total magnetic field intensity in medium number 1 will be equal to h naught into e raised to power minus j k1 yy plus j k1 zz minus rho h naught into e raised to power minus j k1 yy minus j k1 zz multiplied by the unit vector Ax. So we have already discussed in the previous class that the unit vector Ax and the unit vector Ay will be tangential to the interface, and the unit vector Az will be normal to the interface. So the total magnetic field intensity in medium number 1 is tangential to the interface. We go to medium number 2 and we consider the magnetic field intensity of the transmitted wave in medium number 2. So the magnetic field intensity of the transmitted wave in medium number 2 will be equal to tau h naught into e raised to power minus j k1 yy plus j k2 zz multiplied by Ax. Rho is known as the reflection coefficient and tau is known as the transmission coefficient. So this is the magnetic field intensity of the transmitted wave in medium number 2, and as this magnetic field intensity is in the direction of the unit vector Ax, so this magnetic field intensity is tangential to the interface. The unit vector Ay and the unit vector Ax will be tangential to the interface, while the unit vector Az is normal to the interface. So let us apply the boundary condition. The boundary condition states that whenever a wave travels from one medium to another medium, the tangential component of the wave does not change, and the normal component of the magnetic field intensity or the normal component of the wave will change. So you see, the total magnetic field intensity which is in medium number 1 is tangential to the interface. H1 is the total magnetic field intensity in medium number 1, and this H1 is in the direction of the unit vector AX, so H1 is tangential to the interface. Similarly, if we consider the equation for H2, H2 is in the direction of the unit vector AX as well, so H2 is tangential to the interface. So this wave travels from medium number 1 to medium number 2, and as H1 and H2 are tangential to the interface, so according to the boundary condition, H1 will be equal to H2. So we apply the boundary condition, and according to the boundary condition, the tangential component of H1 will be equal to the tangential component of H2. Why? Because whenever a wave travels from one medium to another medium, the tangential component of the wave does not change. However, the normal component of the wave changes. So H1 is in terms of Z and H2 is in terms of Z as well. So we say that this boundary condition will be valid at Z is equal to 0. So if we put the value of Z in equation number in H1 as well as H2, and if we simplify this equation, we get equation number 5. Equation number 5 gives you the relationship between the reflection coefficient and the transmission coefficient. So 1 minus rho will be equal to tau. Now what we do, we calculate the total electric field intensity in medium number 1 and the total electric field intensity in medium number 2. We will apply the boundary condition to the electric field intensity of the wave. We know that whenever a wave travels from one medium to another medium, the tangential component of the electric field intensity will not change. However, the normal component of the electric field intensity will change. So let us calculate E1. In order to calculate E1, we consider this equation of Maxwell. This equation states that the curl of the magnetic field intensity in medium number 1 will be equal to j omega epsilon 1 into E1, and we can calculate E1 from this particular equation. So E1 from this particular equation will be equal to 1 over j omega epsilon 1 multiplied by the curl of the magnetic field intensity in medium number 1. So let us expand this equation number 6. Let us process equation number 6. So E1 is equal to 1 over j omega epsilon 1, and the curl of the magnetic field intensity can be computed with the help of this determinant. So we have the unit vector Ax, the unit vector Ay, the unit vector Az. In the second row of this determinant, we have curly by curly x, curly by curly y, and curly by curly z. Over here, we have the x component of the magnetic field intensity. That is, if we have the x component of H1, we have the y component of H1, and we have the z component of H1. So let us consider H1, the equation for H1. You see, if we consider the equation for H1, here is the equation for H1. And you see H1 has only one component, that is the x component. There is no component along y axis, and there is no component along z axis. So the magnetic field intensity in medium number 1 has got only one component, that is the x component. So here is the x component of H1, the y component of H1 is 0, and the z component of H1 is 0. If we expand this determinant and if we rearrange the right hand side of this equation, we get two components of E1. There will be two components of the total electric field intensity in medium number 1. We see one component will be in the direction of the unit vector AY, and the other component will be in the direction of the unit vector AZ. And the component which is in the direction of the unit vector AZ is the normal component. We are not interested in the normal component of the total electric field intensity in medium number 1. So we just consider the component which is tangential to the interface. So let us consider the equation which is tangential to the interface. We consider the equation of the electric field intensity in medium number 1, which is tangential to the interface. And what we do, we put z is equal to 0 in the tangential component of the electric field intensity as well. If we put z is equal to 0 in the tangential component of E1, so you see here is the tangential component of E1. If z is 0, this component will be 0 and this component will be equal to 0, and you guys can take H naught into e raised to power minus into e raised to power minus jk1 yy, H naught into e raised to power minus jk1 yy is a common quantity. So if we simplify the tangential component of E1, we get equation number 7, which is j h naught into e raised to power minus j k1 yy divided by j omega epsilon 1 into k1z plus rho k1z. So we get the tangential component of E1, and the tangential component of E1 is given in equation number 7. So let us calculate the tangential component of E2. So we can calculate E2 in medium number 2 with the help of the right hand side of this equation. What is on the right hand side of this equation? We have 1 over j omega epsilon 2 into the curl of the magnetic field intensity in medium number 2. So let us put let us put the value of the curl of the magnetic field intensity on the right hand side of this equation. So E2 will be equal to 1 over j omega epsilon 2, and this determinant gives you the curl of the magnetic field intensity H2. So this determinant gives you the curl of the magnetic field intensity in medium number 2. So if we look at this determinant, we have the unit vector Ax, the unit vector Ay, the unit vector Az in the first row. We have curly by curly x, curly by curly y, curly by curly z in the second row, and over here we have the x component of H2, we have the y component of H2, and we have the z component of H2. So if we consider the equation for H2, H2 has got only one component. That is the component which is along x-axis. There is no component along y-axis and no component along z-axis. So here is the equation for H2, and you see H2 has got only one component, that is the x component. There is no component along y-axis and there is no component along z-axis. So this magnetic field intensity has got only one component. So let us go towards the determinant, and you see we have the x component of H2, the y component of H2 is 0, and the z component of H2 is 0. And what is the x component of H2? We have tau H naught into e raised to power minus jk1 yy plus jk2z z. So we expand this determinant and then we rearrange the right hand side of this particular equation. If we do it, we will get two component of the electric field intensity in medium number 2. One component will be along y-axis and the other component will be along z-axis. The component which is along z-axis is normal to the interface. We are not interested in the normal component of E2. Why? Because when the wave travels from medium number 1 to medium number 2, the normal component of the electric field intensity will change. However, the tangential component of the electric field intensity will not change. So here is the tangential component of the electric field intensity, and let us consider the tangential component of the electric field intensity at z is equal to 0. If we put z is equal to 0 in this particular equation, so the term with z over here will become equal to 0. So we consider the tangential component of the electric field intensity in medium number 2 at z is equal to 0. So we get H naught into e raised to power minus jk1 yy divided by omega epsilon 2, and then we have tau k2z. So we apply the boundary condition. The boundary condition states that whenever the wave travels from medium number 1 to medium number 2, the tangential component of the electric field intensity does not change. However, the normal component of the electric field intensity will change. So the tangential component of the electric field intensity in medium number 1 at z is equal to 0 will be equal to the tangential component of the electric field intensity in medium number 2 at z is equal to 0. And if we simplify this equation, the simplification of this equation results in epsilon 2 k1z plus rho k1z, which is equal to epsilon 1 tau k2z. And you see the same equation can be written as we have epsilon 2 k1z plus epsilon 2 rho k1z plus tau epsilon 1 k2z, and we put the value of tau on the right hand side of this equation, and tau is equal to 1 minus rho in this particular case. If we put the value of tau on the right hand side of this equation, we get this particular equation: epsilon 2 k1z plus epsilon 2 rho k1z is equal to epsilon 1 k2z minus rho epsilon 1 k2z. And you see, the same equation will be equal to, we have epsilon 2 rho k1z plus epsilon 1 rho k2z, which is equal to minus epsilon 2 k1z plus epsilon 1 k2z, and we find out the reflection coefficient from this equation. So the reflection coefficient will be equal to minus epsilon 2 k1z plus epsilon 1 k2z divided by epsilon 2 k1z plus epsilon 1 k2z, and this is equation number 9. We know that mu1 is equal to mu naught, and the relative permeability of medium number 1 is 1. Similarly, mu2 is equal to mu naught, and the relative permeability of medium number 2 will be equal to 1. Epsilon 1 is equal to epsilon naught epsilon r1, and epsilon 2 is equal to epsilon naught epsilon r2. Well, we know that the refractive index of medium number 1 is equal to under root mu r1 epsilon r1, but mu r1 is equal to 1, right? So the refractive index of medium number 1 will be equal to under root epsilon r1. Definitely n1 square will be equal to epsilon r1. Similarly, n2 square will be equal to epsilon r2, right? So if we put the values in equation number 9, if we put the values in equation number 9, so equation number 9 can be written as equation number 9 can be written in the form of equation number 10. So the reflection coefficient will be equal to minus n2 square k1z plus n1 square k2z divided by n2 square k1z plus n2 square k2z. This will be the reflection coefficient of the TM wave. We know that k1z is equal to k1 cos of theta I, and k1 is equal to k naught n1. So k1z will be equal to k naught n1 cos theta I. Similarly, k2z will be equal to k naught n2 cos of theta t. If we put the value of k1z and k2z in equation number 10, we put the value of k1z nk2z in equation number 10. So this equation number 10 will give you another equation, and you see the reflection coefficient will be equal to minus n2 square into n1 cos of theta I plus n1 square into n2 into cos of theta t divided by n2 square n1 into cos of theta I plus n1 square n2 into cos of theta t. And if we simplify the right hand side of the reflection coefficient, we get minus n2 square cos of theta I plus n1 n2 cos of theta t divided by n2 square cos of theta I plus n1 n2 into cos of theta t. And if you guys remember, we applied the Snell's law, and we equated n2 cos theta t in the previous class to under root n2 square minus n1 square sine square theta I. So if we replace n2 cos theta t in the previous equation by under root n2 square minus n1 square sine square theta I, so we get another equation. That is the equation for the reflection coefficient of the TM wave, and the reflection coefficient of the TM wave will be equal to minus n2 square cos theta I plus n1 under root n2 square minus n1 square sine square theta I divided by n2 cos of theta I plus n1 under root n2 square minus n1 square sine square theta I. So this is the reflection coefficient of the TM wave. Now you see the reflection coefficient of the TM wave might be a complex quantity. So we will show it in the upcoming classes that the reflection coefficient might be a complex quantity. Anyhow, the reflection coefficient is represented by rho, and the reflectance, which is the ratio of the reflected power to the incident power, will be equal to the square of the absolute value of the reflection coefficient. So we can calculate the reflectance with the help of this particular equation. Now the question rises that can rho be 0, and keep it in your mind that if rho is 0, there will be no reflected wave and there will be no reflection loss, especially in the case when you guys want to feed the light energy from the air to the optical fiber. So if rho is 0, you guys can feed the light energy to the optical fiber without reflection loss. So yes, it is possible to make rho equal to 0. There is an angle which is known as Brewster's angle. The Brewster angle is represented by theta b. So if tangent of theta b is equal to n2 by n1, then this rho will be equal to 0. Rho will be equal to 0 if tangent of this angle theta b is equal to n2 by n1. So under this particular condition, rho will be equal to 0. There will be no reflection loss. Right? So we consider this particular case. We have the fiber over here, and we have the air on this side. This is normal to the interface between the air and fiber. So here is the incident wave, here is the reflected wave, and here is the transmitted wave. So you see, if we feed the light wave through this angle, which is known as the Brewster angle, then there will be no reflection. The reflection will be equal to 0, and the total energy of the incident wave will be transmitted to the fiber. So this is the importance of the Brewster angle. Thank you so much. I shall see you in the upcoming class.